All right, everyone. Day 2 of Parametrics. We're just going to add 2 new components, speed and total distance. So this is not too bad. Works similar to what we've done and things we did first semester. So let's get right to it. Same problem. We have the parametric equations for the x position and the y position represent the path of a car as it drives off a cliff. Find the speed of the car at t equals 2. Okay, so if you remember from last time, remember from last time, fine. What's going on here? No, that's not good. If we graphed this, the car kind of does this type of thing, right? And let's say at time 2, the car's about here. I'm not going to pull it up in Desmos. But at time 2, I want to figure out how fast the car was going, okay? And when we had one-dimensional motion, all we had to do was take the absolute value of velocity. So speed is the absolute value of velocity. But how does this work when we have a velocity vector? Well, here's the idea. Think about the fact that, okay, if I find x prime of t, which is the velocity of the position of x, you get 5. That means at this instant, there's a force pulling me in this direction with a rate of 5 units per unit, whatever it happens to be. Similarly, I can find the vertical rate, and you get negative 10t. So at the same moment, I'm being pulled down in this direction. So I have a horizontal component of my rate, and I have a vertical component of my rate. So for those of you in physics, you understand that speed is a combination of the two. So really, if I could just find kind of what the sum of these two vectors is, which is in this direction, that would give me the speed. So how do you add two vectors together? There's a very nice formula without going too much into detail of why it works. It has to do with the Pythagorean theorem for finding speed, because that distance is the same as the hypotenuse of the triangle connecting these 2 points. But really, all you need to do is know the formula. It's the Pythagorean theorem for both the rates. So you add x prime of t squared plus y prime of t squared at the time you care about. And that's literally it. So that is all you have to do. It is a formula you are going to have to remember. So in other words, if I want to find the speed at time 2, I would plug 2 into the x component and square it. So that's just 5 squared, plus plug 2 into the y component and square it. So I get negative 20 squared, which makes it positive, which when you square both of them and then take the square root, you're going to get a positive answer every time. So your speed is always positive when you do this calculation. And that's really it. It's not too much to it. Just you have to know the formula for speed, which comes from the Pythagorean theorem. Okay, so question 1 done. Second question. Find the total distance the car traveled from 0 to 2. So let's say that this is the distance. Remember, this is literally the path the car takes. So really, all I want to do is measure this distance, because however far this distance is, that's how far the car traveled. So have we ever in this point in this course found a length of a curve like this? And another word for curve is arc. Hopefully you're like, yes, we have found arc length before. We have a formula for arc length. And turns out we have a formula here too for total distance. It's just the arc length formula with a slight variation. Because arc length was 1 plus the derivative squared, and then you take the square root of that and accumulate it. When we have 2 components, we basically need to add both of them together, square them, and then take the square root and accumulate. So it's kind of like you're accumulating the speed at every instant. So if you see the black arrow I drew here, if you could accumulate that plus that, like the speed at every instant, that would give you the total distance. And again, it's going to be positive because total distance is positive. So in other words, all you need to do to find total distance is accumulate the speed from A to B with respect to time. So how does that look as a formula? Well, in this case, if I wanted the speed or the total distance from 0 to 2, that would be the integral from 0 to 2 square root x prime of t squared plus y prime of t squared dt. And you keep everything, that's a really ugly t. That's okay. That's a t. Y prime of t squared dt. And then you just plug everything in and let Desmos do these for you. Or a lot of times, all I want is the setup. So 0 to 2 X prime of t was 5, so again, that's just 5 squared. This one was negative 10t, and we are going to square that, dt. And that's it. That's all you have to do. So these two new components are literally just formulas, and basically they're the same formula, speed, and then you just accumulate speed to get the total distance. All right, so let's take a look at an actual, real-life, legit FRQ on this topic. So parametric FRQs are our friends because they are pretty cut and dry. But let's see for ourselves. All right, so for t is greater than or equal to 0, particles moving along a curve, so its position is given by an x equation and a y equation. Great. At time t equals 2, the position is, that looks like an initial condition, and it has to be both. So we have an x initial condition, and we have a y initial condition. It is known that, look, they are giving you the velocity for the x position, and they're giving you the x movement, and they're giving you the velocity for the y movement. So this is a case where they're not starting you with the position formulas. They're starting you with the rates, which is usually how these work. So is the horizontal, aka the left-right, aka the x movement of the particle to the left or to the right at time 2? Well, if we plug 2 into our rate for the x component, we get square root 2 plus 2 all over e squared, which is 4 squared root of 4 is 2, 2 over e squared, which is positive. So what does that mean if we have positive rate for the x? That means we are moving to the right. Right means positive. So we are moving right because dx dt at x equals 2. Sorry, that should not be x. That should be t equals 2. At t equals 2 is positive, right? Because it's positive. That's it. We could find if it was moving up or down by plugging into this. Sine squared is always positive, so this thing's always moving up, I think. No matter what value t you plug in and you're squaring it, you're always going to get a positive. So this thing's always moving up. It's not a very interesting question. B, find the x coordinate of the particle's position. Okay, so I need to find x of 4. To do that, we're going to do initial condition plus accumulation. Hooray. So what is our initial condition? We have an initial condition at t equals 2. The x position was 5. So we know x of 2, sorry, is that 1? Did I just say 5? 1 plus accumulation. Well, this works the same way we've done it the entire time. Where we're at, where we're trying to get, 2 to 4. And here, we're going to put the velocity of x prime of t, which is dx dt. I'll write it in this notation so it works a little bit nicer. So 4 on the top, 2 on the bottom. And then we're going to accumulate this. Do not try to take this antiderivative by hand because we can't. We could maybe turn it into a series, but we're not going to do that. Instead, we'll let Desmos do it. I know you guys die if you watch me plug things into Desmos, but I don't really care. We're going to do it. You can fast forward if you really want to. Square root of t plus, let's use x plus 2 divided by e to the x dx. Looks good. 1 plus 1.252. 1.252. What did I just say? Something along those lines. 1.25295. Okay, so nothing too different. If we wanted to find the y position, we would do the same thing. We'd use y of 2 in the y accumulation, but we only wanted x in this problem. Find the speed. Okay, so speed we just did in the last problem. To find the speed, all you need to do is take the square root of the x position, the velocity for x, which is square root of t plus 2 over e to the t. But remember, you're plugging in now, since we're finding the speed at 4 instead of 2, or t, we're plugging in 4. Squared plus And then we're plugging 4 into the other one, which is sine squared of 4 squared. And we're going to get that value. Now, let me actually give you some advice when you're going to do these, because we're going to do these with calculators. Do this the same way we did it in and out. In other words, store both equations as two functions. That way you can work with both of them simultaneously. So watch what I mean. I'm going to store f as my dx dt. So just be aware, don't confuse yourself. I'm going to store this function as x, but this f of x, but this is my dx dt equation. I'm going to store this one as my y, but I'm going to call it g of x. So just be very careful about doing this. But if you can keep it straight that, okay, in your calculator, y1 will be dx dt and y2 will be dy dt, then you can just do everything like normal. So to find the speed, all you need to do is do the square root of, I mean, it's probably easier to just plug these into the calculator, get these values from the table. But here in Desmos, I can do f of 4 squared plus g of 4 squared. And that is my speed, 0.57450. 0.57450. Nice. 3 parts done, and we didn't even have to think creatively. We just had to be able to apply the process to each part. Lastly, find the total distance. Cool, we already know that from the previous one. Total distance is just arc length, which is literally the accumulation of the speed from 2 to 4. So you go back to your equation, except you keep this general. And we don't even have to rewrite it. Let's just do x prime of t squared plus y prime of t squared dt. And again, because you have these stored in your calculator, at this point, I can just go back to this x integral 2 to 4 dx. 0.65, this particle barely moved, but that's okay. 0.65098. 0.65098. And that's it. And that's a pretty standard parametrics FRQ. The goal is we're just working with 2 equations and dealing with the motion in 2 dimensions. And it's very much the same as 1 dimension. And that's kind of how calculus works. As you go up to like multi-variable calculus and multiple dimensions, like 3 dimensions or other variables that you're adding, the calculus kind of remains the same. You just start dealing with variables in different ways and it's learning new formulas. But really you're adding on. That's why Calc 1 and Calc 2 are really nice classes to kind of get a good footing for where you're going to be going. So that's it. Pretty short lesson, but really we're just going to practice. So next lesson, next class on Monday, we will, if it's Monday this year, we will practice this FRQs in class. All right, that's it for now. Bye.